the signal that never returned. A signal appears once, clear enough to stand out, structured enough to spark curiosity, strong enough to demand attention. And then the universe goes quiet. No repeat, no second pulse, no confirmation. Just a brief anomaly buried in oceans of noise. In deep space research, this is one of the most unsettling outcomes imaginable. Something registers, something real enough to notice, and then nothing ever comes back. When people imagine space, they imagine silence. In reality, the radio sky is crowded. Radio telescopes do not listen the way we do. They measure electromagnetic radiation across vast frequency ranges. Every observation contains thermal emissions from stars, pulses from neutron stars, radio bursts from magnetars, charged particles spiraling through magnetic fields, the faint glow of the cosmic microwave background, an increasingly human technology. Earth itself is loud. Most of what astronomers record is statistical noise, fluctuating background energy that rises and falls randomly. Signals are buried inside that noise, and extracting them requires mathematics, not intuition. A detection is usually defined as a statistically significant deviation from baseline, a spike above the noise floor, a narrow-band signal confined to a very specific frequency, a pulse that appears too structured to be random. But a single spike is not proof of anything. It is a candidate. Repetition is the dividing line between curiosity and credibility. If a signal returns at the same sky coordinates, with consistent frequency behavior, confidence grows. Astrophysical objects obey predictable physics. Motion produces Doppler drift. Rotation produces periodicity. Orbital mechanics leave signatures in frequency changes over time. If those signatures repeat, we can model them. We can test them. We can eliminate coincidence. But when a signal appears only once, everything remains uncertain. We cannot measure periodicity. We cannot confirm motion. We cannot rule out terrestrial interference. Even genuine cosmic events can be one-off phenomena. Some deep space radio bursts are produced by extreme astrophysical processes, collapsing stars, magnetoflares, violent plasma interactions. They may never repeat. The universe does not guarantee reproducibility. Science, however, depends on it. Earth complicates everything. Our planet is surrounded by an expanding shell of artificial emissions, communication, satellites, aircraft systems, radar installations, ground transmitters, reflected signals bouncing off metal structures in orbit. Even distant objects can briefly align with the telescope's pointing direction and create false positives. Telescopes attempt to filter this contamination. They compare multiple beams to see whether a signal appears in only one direction or many. They check frequency stability and drift rates. They look for polarization patterns consistent with natural sources. They coordinate with other observatories to see whether the signal can be confirmed independently. If another telescope does not detect the same event, suspicion rises. Many high-interest detections ultimately resolve into ordinary explanations, equipment artifacts, processing errors, untracked satellites, terrestrial interference. The more exciting a signal appears, the more aggressively it must be questioned. Modern searches for unusual radio signals are systematic and computationally intense. Petabytes of time-frequency data are processed using Fourier transforms, pattern recognition algorithms, and machine learning classifiers trained to distinguish noise from structure. But this introduces a statistical paradox. When you analyze millions of frequency channels over long durations, rare fluctuations are guaranteed. A 1 in a million anomaly will occur if you look 1,000,000 times. The larger the dataset, the more inevitable statistical outliers become. Thresholds must be set carefully. Too strict, and you risk missing subtle but real phenomena. Too permissive, and false positives multiply endlessly. Researchers walk that boundary constantly. Distance adds another layer of uncertainty. A signal detected today from hundreds of light years away left its source centuries ago. We are not observing the present. We are observing delayed history. If the source was transient, it may have lasted seconds. If it was artificial, it may have been directional, intermittent, or aimed elsewhere. The overlap between their transmission window and our listening window may be vanishingly small. Humanity has only possessed sensitive radio detection capabilities for a fraction of a century. On cosmic timescales, that is barely an instant. The universe may not be silent. We may simply be listening at the wrong moment. Single detections occupy an uncomfortable space between data and imagination. They are strong enough to disturb certainty, but weak enough to deny conclusion. They leave behind timestamps and frequency plots in archival databases, anomalies that cannot be repeated, cannot be confirmed, cannot be dismissed entirely. A signal appears once, a deviation in the noise, a brief structure in the static, then silence. No repetition, no confirmation, no echo. If something is out there, transmitting across the vast dark, maybe the real mystery is not whether signals exist. Maybe the real mystery is timing. We are listening, but the universe does not schedule its events around us.